All right, so this chapter in your textbook is called, this is chapter 7. We went through 1 to 5, chapter 1 through 5, and we're skipping chapter 6. That's called, basically it focuses on an equation called Navier-Stokes differential analysis, which is a little bit more advanced. I think it's covered more in 490, the elective that you can take. So if you're interested in learning more about fluids, definitely take that class. But now we're going to skip over and go to chapter 7. This one is called dimensional analysis. If you remember, in the first week, I talked about dimensional analysis a little bit and making sure we know the units of different physical quantities and their dimensions. That's very important in this chapter. That's all we're going to do here, okay? So we're going to look at the dimensions of different quantities and all of that. Okay, so let's start with just motivating why we need to study this chapter. So far we've looked at analytical solutions of different problems, but unfortunately, only a fraction of problems can be solved analytically. Most of the problems in real world engineering applications, you cannot solve analytically, right? So only a fraction of fluid problems can be solved analytically. And for most problems, what do you think we need to do? If a problem is too complicated, too complex to solve analytically, what do you do? Let's say you want to measure, you want to calculate the force on an airplane wing. Like, how do you do that? Model, someone said? So you can model it, right? And there's two ways to model a problem. One is numerically using CFD, computational fluid dynamics. The other way is you do it experimentally, right? So you set up an experiment. So for most problems, they have to be tested, or most problems, let's write it like that, have to be tested by experiments or CFD. CFD is, again, I think here it's a graduate course. It's computational fluid dynamics. Basically gives you a very powerful set of techniques to solve any fluid problems using a computer. Okay, so we're going to start with one example, a motivating example. Let's say this is the problem you're trying to solve. You want to calculate or analyze the drag force on a sphere. Okay, so there is a uniform flow, say going from left to right, and there is a sphere placed in this flow. And we know, all of us know that if there's a fluid moving and you place an object in that fluid, it will experience some force, right? That force is called the drag, FD, drag force. And now the question is, how does FD change in this? It's a function of what in this problem, right? So what do you think affects this FD? Like if I were to ask you, you can think about this for maybe 30 seconds and then let me know what you think. So what is one thing that's important for us to know about the flow, about the sphere? Yeah. The area of the sphere. So the area of the sphere, or I can just say the diameter, right? So the diameter, which I'm going to show by L. Okay, so the length scale of my problem. So that is, of course, important. It matters if you have a very small sphere or a very large sphere, that will change the drag force. What else? Maybe someone else. Maybe something. So mass will turn out to be not important, right? We're assuming that this is a fixed sphere. So we don't care about the motion of the sphere. You have a fixed sphere. You want to know how much force is acting on it.
The amount, the strength of that force, the blue arrows.
The fluid.
The fluid, yes.
So what do you mean by the strength?
Like, I mean,
it's a fluid flow, right?
Yeah,
so
flow, so the amount of flow, I guess.
So basically you're saying like how strong the flow is or how fast, so the speed of the flow, right? So let's show that by capital U, the horizontal speed, this uniform speed. The viscosity of the fluid, of course, is very important. There will be a huge difference between this being placed in air versus water versus honey, right? So viscosity. One more important density, exactly. So again, that will affect it. It matters if you have a very heavy fluid or a light, low density fluid. Okay, so these are all the variables of our problem. Okay, and figuring out what variables affect your problem, that needs some experience. That's not something that I'm going to ask you. I'm going to tell you that these are the variables of the problems, and then we go from there. So imagine that this is given to you, all of this. You know, U, mu, rho, L are important for FD. And the question is, how does FD depend on these things? Okay, so that's what we're trying to find. And FD here is called output variable. Right? Everything else is the input to the problem. FD is the output. Okay, so what we want is to get FD as a function of rho, mu, u, and L. That's what we're trying to do. Okay, so how do I do this? How do we find this? Let's say we want to do experiments. What kind of experiments do we need to perform to see how FD depends on all of these variables?
That's an experience where you can, first of all, measure that force, and then also where you can just change each of those elements individually.
Exactly. So you want to measure the force, right? While changing just rho. So everything else needs to be kept at a fixed value, right? And you just change rho, for example. So you change the fluid density, and then you do many experiments, right? So because you want to get some kind of curve, something like this. So let's say the first thing we want to study is how F or FD depends on the length, the diameter. So what do? You're going to fix, for example, rho and mu. You're going to fix your fluid, right? And for one length, you're going to get one data, right? One data point. So I'm going to see that for 10 centimeters, FD is this much. I don't know, 5 newtons maybe. Okay. And then I'm going to change the length again, and I'm going to get a different force, right? I'm going to change it again and again and again. So if I have enough points, I will see that, okay, there's this relation between FD and L. It's maybe a nonlinear function like that. Okay, but all of this I have to do for a fixed speed of the flow. So this is all for some velocity like U1. Right, so now I have to change U1 again, and maybe now I get a new curve. I don't know, something like that. And I have to keep doing this, right? And this will just tell me how FD depends on L. now I have to maybe change, let's say, row, right? So again, I don't know what it will look like. Maybe something like this. You're gonna get a curvature. These are arbitrary. You don't need to worry about getting the shape right. And you do this while keeping U, for example, and L fixed and changing mu. So you have mu1, mu2, all of that. So as you can imagine, how many experiments you have to do? A lot, right? You have to do a lot of experiments because you have 5 different variables or 4 input variables, right? And usually, typically, to get a good curve, to get a good function, you need something around like 10 points, okay? So typically, to get a good function, we need around 10 points. So how many experiments do we need to do? We need to do 10,000 experiments. And that's, of course, a lot of experiments. Even numerically, if you're just using the computer, that's going to take forever. And if you're doing actual experiments, there's no way you can do 10,000 experiments, right? So that's the problem we have. When we're doing modeling, this is a big problem. So any questions so far? Okay. Was there a question?
How do you know that what you have, are you picking right there, for like, let's say F, D, and L, are you picking, U and, density to be fixed? Or is that given every time you do F, D, and L?
No, so I'm gonna fix all the other variables, right? And I'm just gonna change the length of the sphere measure force,
Right. but
right?
like,
And then,
So like you picked, well, you changed the flow speed to the flow force itself,
yeah.
and then for the next one, you didn't do that.
Well, here
you
I'm
did-
fixing the other two, right?
Okay.
So this is just an example. In reality, you have to do all combinations,
Okay.
basically.
Got it.
Yes.
Kind of think back. So what we're seeing for each of the presses for like the drag force and length, you can observe the change in flow for those, but you can also on your monitor where you're viewing, view the change in density and the change in viscosity as well, based off of those two variables being our axes.
Yes. So you're saying that you see the effect of this too, for example, here? Is that your
Yeah,
question?
and that what's shown that that variable could be U, could be viscosity, could be L
Yeah.
that we're viewing.
Yes.
It could be either.
It can be anything. Yeah. These are just 2 examples. You're gonna have many more. So you have to have like 5 different curves, okay? Or 4 different, right? So FD is the y-axis, and then you change rho, then you change L, D, mu. And again, for each one, maybe you have to do 10 experiments. So you need like 10,000 experiments, okay? So what we're gonna do, the solution to this is something called dimensional analysis. Luckily, we have a solution. We don't need to do this many experiments. All we have to do is, well, I'm going to show you first what the answer is for this problem, and then I'm going to explain to you how we get to that answer. So first, what is dimensional analysis? It's a method for reducing the number of variables in our problem. And once we do dimensional analysis for this example, from dimensional analysis, we will see in a second that the problem will reduce to FD divided by rho U squared L squared is a function of rho UL divided by mu. So that 5 variable equation problem turns into a 2 variable problem, where now the new variables are these fractions you see. Right, so I just put a combination of variables together in this strange way. We don't know where it's coming from. YFT is divided by that, we don't know that yet. But that's all you need to worry about, that fraction, that group of variables together, okay? So you just have now 2 variables. And in this chapter, we don't really care about the function f. This f here, this is a function that is to be determined by experiments. So that's something that we're not going to do in this class. What we're going to do in this class is learning how to turn the 5 variables into these 2 groups, okay? Okay, so before we do that, I want you to, just a quick reminder for you about dimensions. Can you tell me the dimensions of this thing here, this combination of variables? You might need to write it down. We all remember dimensions. It's different from units, right? Units is, for example, meters. Dimension is length. We have length, mass, time, and temperature. Those are 4 dimensions. Okay. So for example, force is mass times acceleration. So let me do the first one. You do the second one, maybe. Okay, so let's start with this. We want to find the dimensions of this group. So what are the dimensions of force? Does anyone remember? It's mass times acceleration, but what are the dimensions of acceleration? So in terms of units, that's right, but dimensions, it's mass, right, times a length times time to the -2. This is kilograms, meters per second squared, right? Does that make sense? Okay. What about rho? What are the dimensions of rho now? Mass over volume, and volume is a length cubed, so -3 exactly. What about velocity u? Length time -1, and this is squared, right? So I have this 2 exponent. And lastly, the diameter or the length of that sphere, of course, that's just the length. So that's length squared. Now, if you do the calculation, what are the exponents of these dimensions?
Sorry, could you explain why the exponents are negative?
This is like pair, this is mass divided by volume, right?
Oh,
So usually we write
but
it
because
with
you
the
moved it up
negative.
top.
Yes,
Okay.
that's the convention in dimensional analysis. So for example, how many masses are we gonna have after we simplify this? 0, right? So this will be 0. How about length? So you have 1 in the numerator. How many in the denominator? -3 plus 2, right? Plus 2. So that's -3 plus 4, which is 1. And you have 1 in the numerator, so it's 0 again. How about time? Have a -2 on top and -2 here, right? So that's again 0. So you're starting to see what's special about this group of variables that we put together. This is called a dimensionless number, right? Doesn't have any dimensions. Okay, so this is called a dimensionless group or number. It's a way of putting all these dimensional variables together to turn it into something that has no dimension. Make sense? Any questions? So maybe you can now do this other one, and you can probably, you know by now that this should be dimensionless too. So see if you can get something dimensionless from this. Rho UL divided by mu, what are dimensions? If you don't remember the dimensions of mu, I'm gonna help you. Its units are pascals second. So that should tell you the dimension. So dimensions of mu are a force divided by area multiplied by time, right? Pascal is a force per area. So what is force? What are the dimensions of force? It's right here, right? ML. I said force per area. So what are the dimensions of area?
Length squared.
Length squared. And you multiply by time, right? So what does this give us? We will get n L negative 1 t. So this is dimensions of mu. It's used a lot, so you might want to just remember it. Or if you don't remember it, you know that you have this equation, right? Whenever we don't know the dimensions or units of something, we go back to any equation we know. This equation we know tau, which is a force per area, is mu times velocity divided by length. So if you know these dimensions, you can find the dimensions. Any questions? Does that make sense how we got mu? Okay, now that we have mu, plug it in there and see if we get a dimensionless number. Sorry, stop sharing. Okay, a rho was ml to negative 3. U was LT negative 1. L is L, and mu is ML negative 1, T negative 1. So if you look at the number of dimensions, they're all 0, right? So again, you have another dimensionless number. That dimensionless group, the second one, rho UL over mu, that's a very important one. Does anyone know what it's called? This is called the Reynolds number. It's the most important dimensionless number we have in fluids. We're going to talk about it later. It tells you the ratio of inertial force to viscous forces. It will tell you what kind of fluid regime you have, depending on how big it is. If it's very small, you have a different regime. If it's large, you have a totally different. So the physics will change completely. Any questions? So we all agree that these are dimensionless numbers, but we don't know how you get them, right? That's the question. Like, how do I know that these are the two dimensionless numbers in my problem, right? So for that, we have basically a set of, like, you have a set of steps you have to follow. It's like a recipe. Just go through them and it will give you all the dimensionless numbers in your problem, okay? So any questions? Anyone taking notes? Okay, so let's start with this. This is the important part of this class. How do we find the dimensionless groups or variables? And the answer is something called Buckingham pi theorem. Again, this theorem is just a bunch of steps that you follow and it will give you all the dimensionless variables. Okay, so let's see what the steps are. Okay, so step one. Everyone ready? Anyone taking notes? Do you need to go back? Okay. So first thing you do is you list all the pertinent variables in your problem. Okay, so list all the pertinent dimensional variables in the problem. And as I write down each step, I'm going to write down the step for the example we were doing, right? So in the example we were doing, how many dimensional variables we had? 5, right? We had, for this example, we had rho, u, l, mu, and ft, which is the output variable. So the number of these variables, we usually show that by k, and here k is 5. Can be different number for different problems, but here it's 5. Okay. Okay. Next step, you write down all the dimensions of the variables. That's a very important step because we're going to use this in the next step. So basically you just say, okay, I have rho in my problem. I know the dimensions of rho is this, right? I have L in my problem, which is a length. I have U, which is L divided by time. I have mu, which is M L -1 T -1. And we have a force, which is M L T to the -2. Right, so you want to write down the dimensions of these variables. That's the second. And please stop me if you get confused on any step, okay? Very important. Okay, next step is to determine the number of different, sometimes called fundamental, dimensions in your problem. Okay, so basically the dimensions are like building blocks. You want to see how many of these blocks you have. How many did you use to make all of these variables? So how many dimensions do we have in this problem? 3, right? In fluids, the maximum you can get is 4. So all the dimensions that you can have are these. You can have M, L, T, and theta. This is mass. This is length. T is time. And theta is temperature. Usually we don't have theta in this class, but that's like thermodynamics, you have it. Well, we might have it in some examples, but usually we don't. So usually we have 3 MLT, but again, the maximum you can have is 4. Okay? So in this problem, in the example, how many we have? Which ones do we have? Mass, length, time, and that we show by R usually. So R is equal to 3. Which is M, L, and time. Okay. Any questions so far? Okay, next step, step 4, is to choose, this is really, really important, choose something called repeating variables. Okay, and this is, well, for this class, we can say you always choose R repeating variables. So the number of repeating variables will be the same as the fundamental dimensions. So in this example, we need 3 repeating variables. Okay, but what are repeating variables? They can be any variable in your problem as long as they satisfy these conditions. Okay, so the conditions for choosing a repeating variable are the following. First, you don't want it to be the output variable. So for example, in this problem that we're looking at, FD is not a good choice. Okay, it won't break it if you choose it. It could still work, but it doesn't really make sense. You want the output variable to be separate from the repeating variables. The most important condition is that they must not form dimensionless groups among themselves. And this is really, really important. So if you don't, if the chosen repeating variables don't follow that, then it will all just break down. You won't get the right dimensionless groups. Okay, and the last condition is, if possible, you want to select popular variables. And this one is a little like what does popular mean? You'll gain this experience in this class, like which variables are more popular. Usually there are things that are easy to change in an experiment. Things like the flow of, the speed of the flow, right? So things like U, density, you can change the fluid length. Those are usually easier variables to change. But again, I know that 1 and 3 are not that like strong, but 2 is a very strong condition. You want to make sure that 2 is satisfied. Okay, so in this problem, rho in this example, the one we're gonna choose are rho, U, and L. Okay, and I want you to go back and make sure that 2 is satisfied. Is there any way to put rho, U, L together to make them dimensionless? So if we go back to the dimensions of rho, U, L, see if that's possible. Is there any combination of them that is dimensionless? Why not? I see some shaking. Yes.
Time is always gonna exist. Because rho doesn't have time and L doesn't have time.
Right, so we have time
Oh,
only
sorry, I'm
in
looking
U,
at you, sorry.
right? There's no way to combine it with rho and L such that it goes away the time. There's one more dimension that's only the mass, right? Mass is only in rho. So as you can see, but if you choose, for example, rho, U, and FD, there's a way to make it dimensionless, okay? So that's not a good choice. And the other thing is that FD is the output, so usually you don't want to choose that, okay? Any questions? That clear? This is a very important step. If we do all these 4 steps correctly, we're almost done. We have the last step, which is form the pi groups. And pi groups are basically the dimensionless variables. The number of pi groups will be R minus K. Okay, so how many pi groups will we have in this example? What was R? R was 5. Did I? Oh, sorry, this is K minus R, not, yes. K was 5, the total number of variables. R was 3, the dimensions, the fundamental dimension. So how many groups did we get? 2, right? Okay. Okay, so how do I form these groups? So this is what we're gonna do. We're gonna write the repeating variables with unknown exponents then one by one add the remaining variables and find the exponent or exponents that make pi dimensionless. Okay, so what does that mean? Let's see that in practice. We're gonna write the repeating variables. Okay, so first I'm gonna say pi1, the first group, is equal to, what were the repeating variables? In this example? No, the variables, the rho UL. So I'm gonna write them down with some unknown exponent like A, B, C. Okay, they have these powers A, B, C that are unknown. Now, which variables are remaining? Which variables are not repeating variables? Drag force and mu, viscosity, okay? So we're gonna add these one by one. So first I'm gonna add FD. Okay. Right? And now we're gonna solve this. We basically have a system of equations. We're gonna find A, B, C such that that becomes dimensionless. Okay, so let's see how we do that. So we're gonna say, so here we're gonna find A, B, C such that pi1 is dimensionless. Okay, so what we do is we just write down, okay, the dimensions of pi1 is the dimensions of FD. What are the dimensions of FD? Now you go back to step 2 and read the dimensions. Okay, this is why you need to write it down. So can someone tell me? Thank you. Now rho. Someone else maybe? Rho. -3. Don't forget there's an A exponent. U LT -1 with a B exponent and L with a C exponent. Okay, and now you just write down, does this make sense? Any questions so far? So now you basically just count how many masses you have. So can someone tell me how many masses we have? Give me the exponent, like add them. So first we have one mass here plus A, exactly. Right? Any other masses? There's no mass here, there's no mass here. So this has to be equal to 0. We want this to be dimensionless. There should be no mass. Okay, so that's one equation. Next, we have length. Let's count the lengths we have. How many lengths? We have 1 minus 3A. Okay. Plus B plus C. We want no lengths in our dimension, so it should be 0. And lastly, time, -2. No, time is not in this one. Yeah, that's length. Minus B, and that's it. How many unknowns do we have? 3. How many equations? 3, so you can easily solve this. So from the top and bottom equations, we can just directly get A. A is -1, B is -2, and you plug it in here, what do you get? We have 1 plus 3, 4 minus 2, 2, so C is -2. Okay, so pi1, remember pi1 was FD rho A U B L C. So now we found that pi1 is FD, rho to the power of A, which is -1, U to the power of B, which is -2, and L to the power of C, which is -2, or FD divided by rho U squared L squared. So this is our first group. So we found our first dimension. Any questions? This pi has a name. It's a special one. This is called drag coefficient. It's a non-dimensional drag. That's what's called coefficient. So when they do experiments that you read, like papers, like NASA has these, they're not technically papers, but documents online where they talk about the drag of different like winglets and different wings and airfoils. All of them are expressed in terms of something called CD. CD is drag coefficient. They never talk about the drag force. They always talk about the non-dimensional, which is C. Okay? So now what I want you to do is do this last step for pi2 and see if you get that Reynolds number. And once you do that, you're done. Yeah.
The same thing, except we just, instead of putting in FD, we put it in.
Exactly. So what you do is you write down the repeating variables again. So you say pi2 is rho UL with unknown exponents. But what's the other remaining variable? It's mu. So you write mu here and you find ABC such that that's non-dimensional. Okay, so let's do this on the board. You know what you can get, right? You have that in the notes. Anyone need anything from the notes? Should I go back? Which one? Step 3, you said?
I forgot something.
Sure. So is it clear what we're trying to do? You write down the dimensions with the unknown ABC and solve ABC. Yeah. If you get the inverse of rho UL over mu, that's fine. It's still dimensionless, right? You can flip them, you can multiply by a constant, still dimensionless. But they usually write it as rho UL over mu because that's called Reynolds number. It's very famous. You'll get mu over rho UL. Yes. Okay, so I'm gonna start with mu. Remember, it's n L to the -1, c to the -1. We know all of these from step 2. So n L -3, mu L t -1, and L exponent c. Right? Now you just write down all the masses in your system or in your problem, all the length scales, all the times. So mass, we have 1 here, A here, so it's 1 plus A. Length, we have -1 here, -3A, plus B, and plus C has to be 0. And time, -1 and -B. So this first one gives me A equals to -1. This one gives me B is -1. If I plug them in here, we have -1 plus 3 minus 1. That's 2. That's sorry, -1 plus 3. Right? So that's 2. Then minus 1, that's 1. So 1 plus C has to be 0. C is -1. So finally, our pi2, the second dimension of this group, is mu divided by rho UL. But the rho UL over mu, again, it has a name, it's very famous, so usually we can do that. Usually the inverse is used. Which is called the Reynolds number. They just use RE to show that, which is rho UL over mu. And it's very important. Again, we don't have time today, but next time I'll talk about what it means. But this is acceptable. So we say this is pi2. Pi1, we talked about it before. And our problem has now reduced to only 2 variables, right? So now if you do these experiments again, where here you show FD over rho U squared L squared, and here you show rho UL over mu, you see this kind of dependence, something like that. But of course, to get this function, the curve, we don't do that in this class. You need experiments to do that. What we want is to reduce our problem to these 2 variables. Okay, any questions?